Alright guys, welcome back. So this is Unit 3, our non-polynomial differentiation. We're going to take a look at different types of non-polynomial functions, starting with exponential functions and how to take their derivatives. Each one of these will require use of the chain rule, so if you don't know what that means, you need to exit this video and go back to talking about the chain rule process from Unit 2. So the idea is we have an exponential function. The base is either the special number e or a, where a is just any positive rational number that's not e. So like 2 or 3 or 7 or whatever we want it to be. And the exponent is a u that is a differential function of x, meaning that we can take its derivative with respect to x. So the derivative for each of these exponential functions, if it's e to the power of u, your derivative is u prime, the derivative of the exponent, times the original e to the u, which does not change in the slightest. Whereas if it's g of x is a to the u, where a is again that it's a positive rational number that's not e, its derivative is also a u prime, also has an a to the u that's not touched in the slightest, but also includes ln of a, multiplying with all of that. And you can see if you apply this rule to the exponential, if a was an e, ln of e is 1, so it would disappear, leaving just again the u prime times e to the u. So the way it works is, again, very straightforward. F of x is e to the 8x cubed, so my derivative, well, the derivative of the exponent will be 24x squared, and I leave e to the 8x, e raised to the 8x cubed alone. And that's it. That's all the derivative is. Nothing else going on there. That's all I'm doing for my exponential derivative. If it's got a base that's not e, still the same process. I still take the derivative of the exponents, which would be 14x. I then multiply that, though, by ln of the base, so it would be ln of 5. And then I multiply that by the original exponential, 5 to the 7x squared power. This is not a power rule, so the exponent's not decreasing by 1. That's a very common mistake with these exponentials, where you decrease the exponent by 1. Power rule is when it's a variable raised to a number. Exponential is when it's a number raised to a variable. So it's not the same thing in the slightest. So just make sure you're careful with that. And again, so the exponent right now is also just a polynomial. This could easily be other types of non-polynomials we're going to discuss throughout this unit. I didn't include non-polynomials with this yet because, again, we haven't talked about how to do a natural log or a trig or anything like that. So I can't do a 4 to raise to the sine x power. It is something that's possible. Not something we can talk about in this context yet, though. But just apply the same rules. Derivative of the exponent times the original exponential. If the base is not e, then it's times ln of the base as well. Now, we can see this in the context of a product and quotient rule. So again, this is my first function, 8x to the 5th. This is my second function, e to the 6x to the 4th. So our product rule would tell us the derivative of the first function, 40x to the 4th, leave the second function alone, and then plus the first function times the derivative of the second function, where exponential, it's the derivative of the exponent, 24x cubed. And then we leave the exponential alone, e to the 6x to the 4th. So that's our product rule. Now the rest of this is just going to simply be algebraic manipulation to kind of rearrange and rewrite this a little bit. So we have 40x to the 4th, e to the 6x to the 4th. Plus, if we do our 24 times our 8, we get a 192. X to the 8th, and then e to the 6x to the 4th. And then we can recognize that there's a lot of common terms here. The 40 and the 192 both have an 8 in common, so I can pull that out. X to the 4th and x to the 8th both have an x to the 4th in common, so I can pull that out. And they both have this exponential, so I can pull that out as well. Leaving us just simply 5 plus 24 x to the 4th. So that would be the fully simplified version of the answer, and that's what I'm going to look for from you guys in class. It's a very straightforward process right there to kind of factor out and cancel out. And this is kind of why the product rule is very useful. It may have seemed less useful when we talk about only polynomials. So well, I could just FOIL that, and then why would I do a product rule? This is why, because you can't FOIL that original expression, so the only way to take its derivative is to go through the product rule. Our quotient rule, same kind of process here. We're going to have e to the 3x to the 4th over 2x squared plus 3. So we go ahead, and we take our derivative, our quotient rule, tells us to do our low, 2x squared plus 3, d high, which would be 12x cubed e to the 3x to the 4th, minus high, e to the 3x to the 4th, d low, 4x, all over low, which is 12x squared plus 3, and then squared. And 2x squared, sorry, not 12x squared. So from here, we can kind of simplify that a bit more. We can recognize that I'm going to leave it as 12x cubed. Well, no, because I don't want to distribute that 12x cubed into all that, because I'm going to factor the common term they both have. I can see that I've got a 4 and an x in common for both of them and the exponential. So I'm going to take out the 4x e to the 3x to the fourth. Doing so would leave a 3x squared multiplying with my 2x squared plus 3. And it's the full thing on the right side, so it's a minus 1. And then that's all over our 2x squared plus 3 squared. So inside that parentheses, I should distribute. So we have 4x e to the 3x to the fourth on the outside, a 6x to the fourth plus 9x squared minus 1 on the inside. That quadratic can't go any further, so we're not going to worry about it going any further. If we could, then obviously we would deal with that a little bit more. All right, so again, for each one of these questions, you want to make sure you are factoring with the e, because you're going to have an e in the original and with the derivative, so there's always going to be something that can be factored, as well as typically some sort of polynomial expression. This ability to factor is going to allow us to help solve these things a bit more when we start talking about solving these derivatives in Unit 4 and Unit 5. All right, so as our product and quotient rule, we've done chain rule for every one of these. That's how we take the derivative and exponential. We also have the implicit differentiation. So this is where, again, we take a derivative with respect to y, we need a dy dx term. So this would become 6y e to the 3y squared dy dx, because we took the derivative of a y term. 5x becomes 5, 10x squared becomes 20x. So we go ahead and we add over our 5. And then we divide over everything that's not dy dx. So the 6y e to the 3y squared. So we get dy dx to be 20x plus 5 over 6y e to the 3y squared. And that's our dy dx value. So the implicit can still occur and will still occur with these exponential functions. So make sure you're on the lookout for that kind of stuff. So again, everything we did in Unit 2, with the polynomials, we're now going to apply to each of these exponential or each of these non-polynomial functions general for the other 4 videos we got going on for Unit 3. Next up being the logarithms. All right, so as always, I appreciate you watching, and I'll see you next time for those other non-polynomial derivatives.